Hello and welcome to this discussion of the log mean temperature difference. The log mean temperature difference is one of two major methods that we're going to discuss in this class for analyzing or designing heat exchangers. Now, in the previous module, we talked about the energy balance for a heated flow channel and how the temperature of the fluid changes as the fluid flows along the channel. However, in a heat exchanger, we can have the temperature of both fluids change. We have the hot fluid and the cold fluid both moving and changing in temperature. So for that reason, we can't just use one of the fixed temperature differences for heat transfer, like the inlet temperature or exit temperature difference. If we do that, it'll result in overestimating or underestimating the heat transfer. So what we need to do is define an average temperature difference so that we can solve for the total heat transfer. So what we're going to do is start from the energy balance of both fluids. We have the first law here, where MCP delta T for the hot fluid is equal to MCP delta T for the cold fluid. Now we're going to start with the parallel flow heat exchanger because the explanation is a little easier. And then we're going to assume that the system is insulated from surroundings, so there's no heat losses. And we're also going to neglect any changes in the potential or kinetic energy of the fluids. Usually those are very small compared to the changes in thermal energy. Finally, we're going to assume that the specific heat is constant, or really all the properties are constant. So from those assumptions, we can actually derive an expression for the average temperature difference for our heat transfer. And we can do that in terms of the inlet temperature difference and the exit temperature difference. And that's what we call the log mean temperature difference. So this gives us the average temperature difference at which heat transfer occurs in this heat exchanger. Now, for the counterflow heat exchanger, the behavior is slightly different. There's heat transfer between hotter fluids at one end and cooler fluids at the other end. The temperature difference is much more uniform. And in this case, the cold side outlet temperature can be higher than the hot side outlet temperature, so we get more total heat transfer. However, the expression for the log mean temperature difference stays the same. We have to be careful though, because delta T1 and delta T2 are defined a little bit differently. So check the diagram here and make sure you're using the correct temperature differences for your specific heat exchanger design for the log mean temperature difference. Now, we also have to define the overall heat transfer coefficient, or what we call UA. Now, the exact form may be slightly different than the equation given here. This is a very simple version where all you have is convection on both sides and conduction through the wall. We're going to talk about some changes that we can make to this a little bit later on. Now, you can have contact resistances or other factors that get added into this that make the form more complicated, but this is kind of the basic fundamental version of the overall heat transfer coefficient. Now, in this class, when I talk about the overall heat transfer coefficient, I am not referring to U, the capital U in this page. I'm referring to the combination of U and area, or UA. The reason is that UA is going to be a constant, but U may vary depending on where you are inside the heat exchanger. So 1 over UA is going to be equal to 1 over UA for the hot side is going to be equal to 1 over UA for the cold side. And this means that UA cold side is equal to UA hot side. However, if you look at the figure here, the inside of the pipe doesn't have the same area as the outside of the pipe. So the areas are different, so U is not going to be equal. So for this class, when I talk about the heat transfer coefficient, I'm talking about U times A combined. You can also use the linear overall heat transfer coefficient, which is basically U times perimeter. That's for if you don't know the length of the heat exchanger to get perimeter times length as area. If you're trying to find length, then you would use UP times length to get the total, and you would solve for length. Now you can also use the value per unit heat exchanger area, or U. For instance, if you're using R prime or R double prime in the definition here for the overall heat transfer coefficient. This approach is often used in heat exchanger design. For instance, if you need to find out how long your heat exchanger has to be, then length, which is part of the area calculation, is an unknown and you have to solve for it. Now often, the wall resistance, the conduction resistance for the wall, can be neglected in the overall heat transfer coefficient. We call this the thin wall approximation, and we can use that when the conduction resistance is much, much less than the convection resistance, similar to the ideas behind lumped capacitance modeling for transient problems. Now, in some cases, if you have heat transfer from a liquid or to a liquid on one side and heat transfer with a gas on the other side, you can actually neglect the heat transfer resistance of the liquid. And the reason is because the convection coefficient for gases tends to be much less than that for a liquid. So for some heat exchangers, you may only have to care about the convection resistance on one side when you're calculating the overall heat transfer coefficient. But we have to be very careful to make sure of that, rather than just making that assumption. We can also use what we call extended surfaces in order to improve heat transfer to a gas or from a gas. So when we do this, we have to modify the convection resistance, and we do that with what we call the surface efficiency. Here, the heat transfer area for the convection is equal to the total surface area, including the fins. And then the fin efficiency just accounts for the fact that you're increasing the convection resistance through the fins, so it's actually going to slightly reduce the performance compared to the ideal case. So remember, when you have surface efficiency, you use total surface area including fins. And then we get the surface efficiency from the fin area, the total heat transfer area, and what we call the fin efficiency. Fin efficiency can be calculated. We won't be doing that as part of this course, but it is possible to model that. If we do this in this course, if we have extended surfaces, the fin efficiency will be given. We can also use equations based on what we call the fin effectiveness. This approach often makes more sense because it's based on the original heat transfer area, so we don't need to modify the surface area in our heat exchanger calculations. We just use the cross-sectional area of a single fin, which is A sub c, and then the base area, or the area of the original heat transfer surface, which is A sub b. We can also relate fin effectiveness to fin efficiency through a couple different equations. So if we do any problems using fins, fin effectiveness or fin efficiency will be given, and these equations will be provided to you so that you don't have to memorize them. We also need to account for fouling factors. Fouling factors are essentially a type of contact resistance. In real systems, dirt or corrosion can reduce the heat transfer between the fluid and the surface. And that's what produces these fouling factors. There's not really any way to predict it, so we often just perform experiments to measure it. And there's some representative values here in this table on the slide, but for the most part, if there's a fouling factor present, it will be given to you. There's not going to be a model or anything like that. Now, we've talked about a bunch of things related to this log mean temperature difference approach. However, there are some shortcomings. It's very useful, but it requires that we know the inlet and the exit temperatures from the beginning. Now, this can sometimes be true for engineering calculations. For instance, if you have a condenser or a feed water heater or something like that, and you know the design requirements, the required inlet and exit temperatures and flow rates and so on, then you can calculate the heat transfer rate very easily. But if you only know the inlet conditions and not the exit conditions, then you have to guess delta T2, and so it becomes a long iterative process. So it's not always that good of a design tool for that kind of behavior. However, we're going to talk about effectiveness NTU, which is a little bit more effective for that type of analysis in another presentation.